You're welcome to Excellent Simplified Tutorials.
Alright, so we are going to look at the second section of this past question. Now, the question on the board says, show diagrammatically the carboxylation of acetyl-CoA to malonyl-CoA from biotin and carboxybiotin. Now, to answer this question, you need to know the structure of acetyl-CoA, which I've done in my previous video. So go to that video and check. Now, the structure of acetyl-CoA is this is the structure of acetyl-CoA. Now, the question requires us to show the carboxylation. Now, carboxylation means addition of carboxylic acid group. So, carboxylation of acetyl-CoA, meaning we are going to add carboxylic acid to acetyl-CoA to form malonyl-CoA from biotin and carboxybiotin. Now, biotin there is just serving as a coenzyme. So, let's look at how we can do that. So, first, you have to show diagrammatically, so you are not using their names but their structures. So to answer that question, acetyl-CoA will be converted to, now take note that CO2 is coming in. CO2 is coming in because it's a carboxylation reaction. And the name of the enzyme, very, very important. Now, any reaction you're writing, you must write the name of the enzyme, because that's the most important thing. If you just write the reaction without showing the enzyme catalyzing that reaction, your reaction is not complete. So the name of the enzyme that will catalyze this reaction is called acetyl-CoA carboxylase. Acetyl-CoA carboxylase. Acetyl-CoA carboxylase. So if CO2 gets attached to this, now this is what is going to happen. I'm going to draw this acetyl-CoA back and we'll see how that is done. So this is my acetyl-CoA. Now to attach my carboxylic acid group to this, remember this CO2 is the same thing as writing it this way. This is it. Now to attach it, remember carbon is tetravalent, so we have to remove one hydrogen. And we'll get this. This is our malonyl-CoA. This is malonyl, from here acetyl-CoA. And this is malonyl-CoA. So this is what you are required to do. The carboxylation of acetyl-CoA to malonyl-CoA. This is the solution to that question. So let's look at the next question. The question says, why is acetyl-CoA carboxylase system considered as one of the most likely sites of regulation of fatty acids? Now, from the previous question, which is still on the board, we saw that acetyl-CoA carboxylase catalyzed the reaction from acetyl-CoA to malonyl-CoA. Now, the question is asking, why is acetyl-CoA carboxylase system considered as one of the most likely sites of regulation of fatty acids? Now, this is a rate limiting step in fatty acid synthesis. And acetyl-CoA carboxylase catalyzes the limiting step, the committed step. It's either you call it the rate limiting step or the committed step in fatty acid synthesis. So since it catalyzes the rate limiting step in fatty acid synthesis, that enzyme acetyl-CoA carboxylase is a likely site of regulation, because now this determines if fatty acid synthesis will take place or not. So because it catalyzes the rate limiting step, that is why it is considered as one of the likely sites of regulation of fatty acids. Alright, next question. The dehydrogenation step facilitated by FADH2 during the beta oxidation of fatty acid is catalyzed by dash. The dehydrogenation step facilitated by FADH2 during the beta oxidation of fatty acid is catalyzed by dash. Now, for us to be able to answer this question, we need to have an idea of beta oxidation. Now, beta oxidation, we are breaking down fatty acid. We are breaking down fatty acid. And when fatty acid is broken down, the end product of fatty acid breakdown is acetyl-CoA. It's acetyl-CoA. Now, how do we break down fatty acid? Now, let's look at this pathway. Let's use this pathway to elucidate that. Fatty acid is first activated to fatty acyl-CoA. So the first thing we're having here is fatty acyl-CoA. This is the activated form of the fatty acid. Now, the fatty acyl-CoA undergoes the beta oxidation in 4 steps. The first step here is called dehydrogenation. Dehydrogenation, which is removal of hydrogen. You can also call that oxidation. And the coenzyme that is facilitating this reaction is FAD. And in the process, FAD is reduced to FADH2. The name of the enzyme catalyzing this reaction is acyl-CoA dehydrogenase. So if fatty acyl-CoA is oxidized, what we have is now trans-2-enoyl-CoA, meaning a double bond is placed on position 2 of fatty acid. I'll use diagram to illustrate that, but let's take it to the end first. Now, from trans-2-enoyl-CoA, enoyl-CoA hydratase, the second reaction now, which is called hydration reaction. This enzyme adds water, and you agree with me that water is H2O. That is HOH. So H is added on one side of the double bond, OH is added on another side of the double bond, and we have beta hydroxyacyl-CoA. The next step of the reaction, which is oxidation reaction, oxidation by NAD, we'll have beta ketoacyl-CoA. Then the last step, theolysis. The beta ketoacyl-CoA will be broken down to release acyl-CoA, another acyl-CoA that is short with 2 carbon, and acetyl-CoA. Acetyl-CoA is given up. Now this acyl-CoA can undergo another round of the beta oxidation until they are all broken down to acetyl-CoA. Now let me use diagram to illustrate what I just said before we go back to the equation. Now fatty acyl-CoA, let's use this. This is our fatty acyl-CoA. Now this is our fatty acyl-CoA, and the first step, which we say is dehydrogenation. If I'm numbering this is my carbon 1, 2, 3, right? Carbon 1, 2, 3. Dehydrogenation means removal of hydrogen. So one hydrogen is removed on position 2 and position 3. Carbon 2 and carbon 3. So if I remove that, what I will have now is something like this. But carbon needs to have 4 bonds, and we're having just 3 bonds here. So we add a double bond in between to complete the tetravalency of carbon. Now what we now have here is called trans-2-enoyl-CoA. Enoyl-CoA because this carbonyl carbon is connected to a carbon with double bond. So we call it trans-2-enoyl-CoA. That 2 shows that the double bond is on carbon 2. Trans-2-enoyl-CoA. Good. Now the next step is hydration, addition of water. And water is HOH, H2O. So what will happen is we'll add hydrogen, this hydrogen on carbon 2 and OH on carbon 3 to remove the double bond. So the next step will be ROCH. Now this is it. We add OH here and we'll add hydrogen here. So this is our beta hydroxyacyl-CoA. It is called beta because the hydroxy group is on the beta carbon. Now to count this, an alpha carbon is a carbon after the carbonyl carbon, after the functional group. So this is my alpha carbon and this is my beta carbon. This is my alpha carbon and this is my beta carbon. So since the hydroxy group is on the beta carbon, we call it beta hydroxyacyl-CoA. Now the next step is oxidation by NAD. This hydroxy group here is oxidized to a ketone, and we'll have something like this. We'll have something like this. So we no longer call this beta hydroxy, but we'll call it beta keto because the ketone functional group now is now on the beta carbon. So beta ketoacyl-CoA. The next thing is this compound will be broken down. Remember, we call it beta oxidation, meaning we are oxidizing on the beta carbon. Then theolysis. Theolysis will come in and break down this bond. If you notice from here, coenzyme A was coming in, CoH was coming in. So if you break down this part here is the acetyl-CoA. This is the acetyl-CoA, and this part here, our coenzyme A, our CoH, we attach here, and we have our acyl-CoA, our fatty acyl-CoA. This one will continue to undergo the breakdown, beta oxidation, until they are all converted to acetyl-CoA. Very good. Now, back to the question. The question says the dehydrogenation step facilitated by FADH2 during the beta oxidation of fatty acid is catalyzed by, I guess you already know the answer, because we said we have 4 steps. Dehydrogenation, which is the first step. The second step is hydration. The third step is oxidation, and the last step is thermolysis. So the answer to that question here is simply acyl-CoA dehydrogenase, because that is what is catalyzing the dehydrogenation reaction facilitated by FADH2. So the name of the enzyme, which is the answer to this question, is acyl-CoA dehydrogenase. Acyl-CoA dehydrogenase. If you need a broad explanation of this beta oxidation, the video is already on my channel, so you can go through it and watch, so you have in-depth knowledge of this beta oxidation of fatty acids. All right, the next question. The next question says the breakdown of eicosanoic acid in the beta oxidation cycle will yield dash and dash molecules of NADH and FADH2 respectively. This NADH and FADH2 respectively. Now the first thing is to note, what is eicosanoic acid? We know eicosanoic acid is a fatty acid actually, but how many carbon fatty acid? Now eicosanoic acid have 20 carbon. Now if eicosanoic acid goes through the beta oxidation pathway, which is still on the board, beta oxidation pathway, how many FADH2 and how many NADH are we going to produce? Now if you notice from this pathway on the board here, this is just one cycle of beta oxidation, and if you notice, we produce, for each cycle we produce one FADH2 and one NADH. Now if the fatty acid is 20 carbon, like in this case 20 carbon, remember that the first beta oxidation will produce one acetyl-CoA, right? We'll produce one acetyl-CoA, and the acetyl-CoA is 2 carbon, so we've removed 2 carbon. We are left with 18 carbons. If we go on again, another beta oxidation, we produce another acetyl-CoA. Let me use AC for acetyl-CoA, and we are left with just 16 carbon. If we go on again, the next cycle, we'll remove another acetyl-CoA, and we're left with how many carbon? 14, right? 14 carbon. If we go on the next one, acetyl-CoA will be given off, and we are left with 12. The next one will be left with 10. The next one will be left with 8. The next one will be left with 6. The next one will be left with 4. And the last one will be left with the last acetyl-CoA. Now, how many cycles of beta oxidation did we undergo? Now, how many acetyl-CoA did we produce? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's as simple as dividing 20 by 2, since acetyl-CoA is 2 carbon. So we produce 10 acetyl-CoA, but we have just 9 rounds. 9 rounds, if you count 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 rounds. This will be strenuous if the number of carbon is high. All you have to do is, if you are given the number of carbon, after knowing the number of carbon, 20, divide by 2. That will give you 10. That is the number of acetyl-CoA. Now, to know the number of rounds of beta oxidation is just minus 1 of the number of acetyl-CoA. So in this eicosanoic acid, we went 9 rounds. 9 rounds. And remember, for each round, we were producing 1 FADH and 1 FADH2 and 1 NADH. So since it is 9 rounds, how many NADH are we going to produce? For 1 round, we produce just 1 NADH. For the second round, we'll produce 2. So for 9 rounds, how many did we produce? 9, right? 9 NADH. For FADH2, since 1 cycle gave us just 1 FADH2, 9 cycle will give us 9 FADH2. So the question says the breakdown of eicosanoic acid in the beta oxidation cycle will yield dash and dash molecules of NADH, NADH and FADH2 respectively. So the answer here is simply 8 and 8. 8 and 8. Since, 9 and 9. Please take note of that correction. 9 because we are going 9 rounds. 9 rounds. Now let me give you an assignment. Drop the answer in the comment section. If we have a fatty acid of 26 carbon, the fatty acid have 26 carbon, how many NADH and how many FADH2 are we going to produce from 26 carbon fatty acid?